There's another extremely important pathway called the salvage pathway. In essence, what the salvage pathway is about taking, so purines, let's say you have AMP in the cell or GTP, ATP, and so on in the cell that's been used, and it's going to be degraded. Okay? Purines, like any other molecule, get degraded. In their degradation pathway, there are intermediates that are formed. So the salvage pathway, in essence, is to capture these intermediates and recycle them back to form the original purine or purine nucleotide, which is either IMP, AMP, and GMP. Okay? So that's in essence what the salvage pathway. It's really important, extremely important, and you'll appreciate why it's important in a minute. So there are two enzymes that do that. Hypoxanthine, okay, guanine. These are the nitrogenous bases you find in IMP and GMP. So hypoxanthine guanine phosphoribosyl transferase, abbreviated HGPRT. That's an very important enzyme in the salvage pathway. This has nothing to do with de novo synthesis. This is recycling intermediates from purine degradation. And another one called adenine phosphoribosyl transferase, APRT, specific for adenine nitrogenous bases. So this is what the salvage pathway looks like. Here's hypoxanthine. As you can see, it's a purine base. It's really an intermediate in the degradation of IMP. Here's guanine. It's an intermediate in the degradation of GMP. So instead of degrading these guys all the way to a molecule called uric acid, you catch them and recycle them. So if you reattach this hypoxanthine to a phosphoribose from PRPP, that's PRPP, you get IMP. If you reattach guanine to phosphoribose, you get GMP. And if you reattach adenine to PRPP, you get AMP. This salvage pathway is extremely important because in humans, we actually salvage about 80% of what we make. That means we only degrade about 20% of the purine nucleotides that we make. The other 80% are recycled through these pathways. Okay? Hence the importance of this pathway. And actually, there's an inherited deficiency here in this enzyme called HGPRT. And that inherited deficiency affecting just those two nucleotides, the guanine and hypoxanthine, results in a pretty serious condition called Lesch-Nyhan syndrome. One of its hallmarks is self-mutilation, hyperuricemia, and mental retardation, all important consequences of this deficiency. Okay? So just know the deficiency. So hyperuricemia results in a condition called gout. So because these children, this is actually occurs, these manifestations happen pretty early on. So you have self-mutilation, they're like by the age, once they are teething and have some teeth, they start biting their fingers, their toes, whatever, their lips. Self-mutilation is one manifestation, and the Other one is mental retardation and hyperuricemia. The final degradative product of all purines is uric acid. Okay? So when you degrade your all purines, you get uric acid. The importance of this enzyme is it captures hypoxanthine and guanine, so you don't form uric acid and you recycle them. But because this enzyme is deficient, you're going to have excess uric acid formation in these children. Uric acid is sparingly water soluble, or has a limited solubility in water. So as it accumulates, as it increases in the blood or in the urine, it's going to crystallize, form crystals. Some of these crystals will be found in the diapers as orange crystals in the urine, and they also can make their way to synovial fluids in the joints, and they create this sort of an arthritic pain due to the hyperuricemia. Okay, so you just need to know the enzyme and the outcome of its deficiency. So key things: severe mental retardation, self-mutilation, and gout is the same as hyperuricemia. If you like this video, please subscribe. Thank you.